Do you want to give your image models a boost by simply tweaking your input data? Today, I'll show you how to perform image augmentation. Using Albumentations, you can transform your images in a flash. So, image augmentation or data augmentation is a very popular concept in the field of computer vision. Why? Because it helps reduce overfitting in your image model and helps you simulate different environments. If you're working on building an image model from scratch, you shouldn't expect your data in the real world once you've deployed the model to be perfectly aligned to your training dataset. So the images that you receive in the real world could have a lot of noise, could be distorted, could be blurry, could be cropped, could be rotated. There could be many changes to the data that you actually receive when compared to your training dataset. Well, how do you handle this when you train your image model? So this can be achieved through image augmentation. So image augmentation is a process of manually tweaking your input data by adding noise, distortions, blurriness, maybe rotating your inputs to basically mimic the real world scenario. So since we now know why image augmentation is crucial for your image models, I will show you how we can integrate Albumentations to perform data augmentation. So without further ado, let's get right into the tutorial. Alright, so let's start by installing Albumentations. So it's very simple. All you need to do is just run pip install Albumentations, and let's just do it right now. Well, that was quick, it took 2 seconds. So now let's just import whatever functions we need from Albumentations and OpenCV and Matplotlib for visualization purposes. Also, since nobody wants to type Albumentations every time you reference this library, I've cast it as an alias called A. Next up, this is what you have been waiting for. We have the transform variable, which is the augmentation pipeline. So Albumentations, they provide a function called compose, which takes in a list of augmentations that you can perform for your input dataset. Alright, so this list is just a small subset of what you can actually do with this library. I've picked and chose some of the functions that they provide. The complete list is in the documentation page, which I've linked down in the description. So let's go through all of these transforms one by one. So we start with the horizontal flip, which basically randomly flips a training input image with a probability of 50%. I also randomly rotate the image by 90 degrees with a probability of 0.5 or 50%. And also I increase the brightness contrast, but this time a probability of just 30% of happening, and blur the image again with a blur limit of 3 with a probability of 30%, and a random crop. Basically I'll crop the image with a fixed height and width of 256 cross 256 pixels, and this also has probability of 30% of happening. So you may see something interesting here that I've commented out the a.normalize function. So in the real world, when you train your image model, you will pass in your augmented image to a pre-trained model. So what a.normalize does is that it normalizes the pixels in the format expected by these pre-trained models. So when you copy paste, or if you use this code when you run your actual training, please make sure to uncomment the a.normalize function. So this helps standardize the input to the model. For now, I've commented it out for visualization purposes, which you will see down below. So with that being said, let's define the transform class by running this cell. So it's done. Alright, so I've passed in a sample JPG file for today's tutorial, and I will read this image into memory using the OpenCV library. All you need to do is just use the imread function and pass in the path to the sample JPG file. And on top of that, I use CVT color to make sure that this is in an RGB format. So all you need to do is just run the cell, and now we have the image loaded to memory. Alright, so let's start by building the visualize transform function that we will be using to visualize the augmentations. So we'll start by defining the function name and the inputs to the function, which is the original image, the transform pipeline variable that we have defined before, and the number of examples. So I want to have 5 images per row. Next up, I define the subplot function. So I want 2 rows with 5 images each. On the top row, I want to have the original image, and on the bottom row, I want to have the augmented image for visualization. Alright, so I loop through each column, which contains 5 examples each, and then I get the augmented image by calling the transform pipeline. All that the transform augmentation pipeline needs is the input image, and the image key, which gets returned after calling the transform, contains the augmented image. So in the first row, I will have the original image. So I just do access.imshow with the original image that is passed in, and I set the title to original for obviously for readability. Also, I check if the augmented image that is returned by the Albumentations library has a permute key. So why is this required? Because Matplotlib expects the image to be arranged in the format of height, width, and channels. But sometimes the augmented image comes in the format of channels, height and width. So in case it is that in that format, we have the permute key available to see if it is actually permuted, and then we rearrange the image in the format matplotlib requires for visualization. And of course, once we have the augmented image in the correct format of channels, height and width, we then plot the axis, plot the subplot in the second row, which is the augmented image, and we set the title to augmented for readability purposes. And then we call the plot.show function in order to show the actual rows and columns. Alright, so now since we have the visualize transform function, let's run the cell. Alright, so now is the moment that I've been waiting for. So let's call the visualize transform function, passing in the image and transform object and the number of examples, which is 5 images per row. So let's just run this and see what's happening. So as you can see, the original images are plotted on the first row and the augmented images are plotted on the second row. So the first image, there you don't see any change to the output because the probability of happening varies between 30% and 50%. But in this one, you see that the image, in the second one, you see that the image has been flipped. Third one, the image has been flipped. The fourth one, the image is the same. Fifth one, there is a small change in the brightness. So you can see that the augmented image is a bit darker when compared to the original image. Let's run it again and see what's happening. Alright, so we have some more changes. So we have the last image which has been rotated by 90 degrees. We have an image that has been blurred with the max blur of 3 as we have defined previously. And there's another image that has been cropped as well. So this is how you'd expect the images in the real world to be. It will not be perfect as how the original image looks like. So in order to add noise manually, this is exactly why we perform data augmentation. This will reduce your model's overfitting and help it perform much better in the real world. So that brings us to the end of today's tutorial. As you can see, Albumentations is very easy to set up and integrate with your image model's training pipeline. As usual, I've pasted the link down below for the written blog for your reference and for those who prefer reading. And if you found this video helpful, please do leave a like, comment and subscribe. It truly means the world to me. So with that being said, thank you so much for watching and see you in the next one.